In this video, we're going to take a look at rates of change and the tangent to a curve. So I wanted to start with a definition of an average speed. So if we have a function f of x, which represents a position function, then the average speed over the interval x1 to x2 is given by change in y over the change in x, which represents change in the position divided by change in time, which is f of x2 minus f of x1 over x2 minus x1. So again, this calculates an average speed over the interval from x1 to x2. What we would like to do is to be able to come up with a formula to find an instantaneous speed or an instantaneous rate of change. To do that, I want to first give some definitions and draw some pictures, and then we will get a nice formula to solve that problem. So let's define a few words here. If we have some function here, then a secant line is a line that goes through 2 points on the function. And at each of those points, it crosses through the function at both points. A tangent line is a line that just touches your function at that single point, but does not cross through near that point. It may, perhaps, if this function continues up here, off straight up, this tangent line may run into that function again later on, but we only care that it just touches and kind of bounces off the function at that given point. And if that happens, it is a tangent line at that particular point. So just some quick definitions there on when I discuss secant line or tangent line. Okay, so now let's draw another picture. We're going to call this function f of x. We have our x-axis and our y-axis here. And what we want to do, our goal, is to find an instantaneous rate of change, or if this is a position function, an instantaneous speed. So I'm going to draw a tangent line at some point here, which we're going to call x comma f of x, or x1 comma f of x1. But I'm going to draw another point over here, which we're going to call x2 comma f of x2. And I'm going to draw this secant line. And now what we notice is we're trying to find the slope of this tangent line, which represents a rate of change or an instantaneous slope of your curve f of x here at that given point. Well, to find the slope of a line, we need to know 2 points generally. Unfortunately for this tangent line, we only know that single point. So how do we find the slope of this tangent line? Well, we draw out our secant line here, one example of a secant line, and we can find the slope of this secant line. Unfortunately, it's not very close to the slope of this tangent line, so that seemingly doesn't help us at the beginning. But if we draw another secant line here, where our second point is moved a little closer, And then we draw another point here where our secant line is moved a little closer. Then what we see is that the limit of these slopes approaches the slope of this tangent line. So the slopes of these secant lines approach the slope of the tangent line, right? As we make new secant lines, the slopes of these secant lines gets closer and closer and closer to the slope of that original tangent line. So we do have an idea here of how we can calculate the slope of that tangent line via these slopes of these secant lines. So notice that we have a similar formula for what we had just written out. So let's write this out. The average rate of change of y equal to f of x with respect to x over the interval x1 to x2 is change in y over change in x is f of x2 minus f of x1 all over x2 minus x1. So, right, this is our same formula that we wrote down for the average speed earlier. So really, these are the same problem. So, again, what we're trying to do is find the slope of this tangent line. And we can do that by estimating slopes of secant lines as the second point here approaches the first point. So I want to write that out a little bit more carefully on another picture. And then we'll be able to get a formula for our instantaneous velocity or an instantaneous rate of change. So let's draw out that same picture. We have our tangent line here. And we have our secant line. And then we can actually build a triangle between those 2 points. And we recognize that if we call this point x comma f of x, and if we call this point x plus h comma f of x plus h, where h is just our horizontal change here, which is equal to, if this was x2 and x1, this is really just x2 minus x1 is this change, h. So if we write this out, and we write out our formula from before, then change in y over change in x, which was f of x2 minus f of x1, all over x2 minus x1. Well, let's replace x2 with x plus h here. So this is f of x plus h minus f of x all over x plus h minus x, which is f of x plus h minus f of x all over h. So we get a nice formula here that is the slope of a secant line with a change in your horizontal distance of h. So that's your length of your interval. And of course we want that to have h not equal to 0 because we can't have 0 in the denominator. But our formula then for finding the instantaneous rate of change, or this slope of this tangent line, is to take this formula and we let the h approach 0. So if this value of h approaches 0, then the average rate of change approaches the instantaneous rate of change. And this right here is going to be the expression that we're going to use to solve this kind of a problem. But unfortunately, to actually work out some details here, we need to formally define a limit and learn how to calculate those. And that will all come in our next video. So this is where we want to end that first video on rates of change and tangent lines.